Welcome to the deep dive. Today, we're going to pull back the curtain on some truly invisible orchestrators that power so much of our modern world. Real-time operating systems, or RTOS. You might not have heard that specific term often, but trust me, they're everywhere, silently making sure critical systems respond exactly when they're supposed to.
That's spot on, yeah. If you've ever flown in an airplane, driven a modern car, or used a, cutting-edge medical device, you've definitely interacted with an RTOS.
Right.
What's fundamentally different about them compared to, say, the operating systems on your laptop or phone is their very specific, very rigorous purpose.
Okay, so our mission for this deep dive is to truly understand what an RTOS is, how it achieves that incredible precision, where it's absolutely essential, and what makes some of the leading options unique.
Sounds good.
Think of it as a shortcut to understanding the precise, time-sensitive heartbeat of embedded technology. Let's unpack this. So to start us off, what exactly is an RTOS? We know it's an operating system, but what makes it real-time?
Well, at its core, an RTOS is built to manage and react to inputs or events within guaranteed, strictly defined timeframes. The absolute key word here is guaranteed.
Guaranteed, okay.
Unlike the general-purpose operating systems you use every day, an RTOS prioritizes deterministic behavior and predictable responses above, well, pretty much everything else.
Deterministic, what does that mean in practice?
It means, imagine a system where for any given input, you not only know the output, but you know exactly when it will arrive every single time. That's determinism.
Ah, okay, like clockwork.
Exactly. It means tasks execute with remarkable consistency and timing. The maximum time for critical operations is known and, crucially, guaranteed. This is vital in situations where even a tiny delay could spell disaster.
Right.
They also aim for incredibly low latency, minimizing the delay between an event happening and the system's reaction, often through rapid interrupt processing. And because they're often in mission-critical environments, unwavering reliability is non-negotiable. Plus, given they often run on very resource-constrained embedded systems.
Like tiny chips.
Yeah, exactly. Efficiency is paramount. Think tiny memory footprints, optimize CPU use. While they multitask, create the appearance of many things happening at once. It's all about sharing CPU time predictably and within strict deadlines, ensuring vital tasks complete on time every time.
That's a powerful distinction. So if an RTOS is all about guaranteed timing, how does that fundamentally change its internal workings compared to the general-purpose operating systems we use every day, like, say, Windows or Linux?
It's truly a different philosophy. General-purpose operating systems, or GPOS, they're designed for flexibility, a smooth user experience, right?
Yeah, mostly.
They use what's called fair scheduling, meaning they might boost a low-priority task just to keep your desktop feeling responsive, which introduces variable delays.
Okay, I think I see that sometimes.
An RTOS, on the other hand, uses deterministic priority-based scheduling. If a high-priority task needs the processor, it gets it immediately. Lower-priority tasks simply wait, no matter what.
So no fairness if something critical is happening. Sounds pretty intense.
It has to be, for certain applications.
What about something called jitter? I hear that term in this context sometimes.
Jitter. Yeah. Jitter is like a tiny, unpredictable wobble in timing. Imagine a task that's supposed to happen exactly every 10 milliseconds.
Okay.
If it sometimes happens at 9.9 meters, sometimes at 10.1 meters, that variation is jitter.
Got it.
GPOS has higher jitter, which is fine for maybe streaming video, but for an RTOS, minimizing jitter is crucial. Think of anti-lock brakes.
Right. You need precision.
You need consistent, precise execution every single time. And the consequences of a missed deadline, well, that's the ultimate differentiator.
How so?
For a GPOS, a missed deadline might mean a slow web page or maybe a frozen app. Annoying, sure, but generally harmless.
Yeah, it happens all the time.
But for an RTOS, a missed deadline can be catastrophic equipment damage, severe financial loss, or in the worst cases, loss of human life.
Wow. Okay.
This fundamental difference in consequence drives every single design decision.
So it's a fundamental trade-off then. General flexibility and features versus guaranteed timing and, I guess, resource efficiency. That difference really sets the stage for where these systems are used. So how do these specialized operating systems actually achieve that incredible precision and reliability? What's going on inside an RTOS to make that happen? What's under the hood?
Right. Well, the core architecture is meticulously engineered.
Right.
You can think of it as several key components working together in concert to enable those real-time capabilities.
Okay.
First up, you've got the kernel. This is the foundational core, managing crucial resources like scheduling and memory.
The heart of the OS.
Exactly.
Yeah.
Historically, many RTOS used a monolithic kernel, where the entire OS was essentially a single large program.
Right.
But the real genius, I think, of the microkernel approach, seen in RTOS like QNX Neutrino,
QNX, right. I've heard that one.
is its ability to create these like impenetrable walls between software components. Imagine a critical system like an airplane's flight controls. If one minor subsystem crashes, you absolutely cannot have it take down the entire plane.
Definitely not.
Microkernels are specifically designed to prevent that kind of catastrophic domino effect. They isolate failures and provide really robust memory protection. This is a huge evolutionary step in RTOS design, bringing advanced reliability and security features, what's mostly found in GPOS, to these high-assurance safety-critical systems.
That isolation sounds crucial.
It is. Then you have task management and scheduling. Tasks, or sometimes called threads, are the fundamental execution units. Each is assigned a priority, and the RTOS scheduler ensures the highest priority ready task is always the one running.
Always the most important thing first.
Precisely. Most RTOSs use preemptive scheduling, meaning a higher priority task can literally interrupt a lower priority one for immediate response. It's all about rapid response.
Okay.
Now, while the RTOS provides these powerful tools, true determinism requires careful design by the developers to prevent issues like priority inversion.
Priority inversion. What's that?
That's where a high-priority task gets accidentally blocked by a low-priority one that happens to be holding a resource the high-priority task needs.
So the important task gets stuck waiting for a less important one.
Exactly. It's a classic problem. So RTOS often include mechanisms like mutexes with priority inheritance to mitigate this, to sort of temporarily boost the low-priority task so it gets out of the way quickly.
Okay, that makes sense. Clever.
Beyond scheduling, you have inter-task communication and synchronization. These are crucial for tasks to interact safely without corrupting data. Think of them as the nervous system of the RTOS.
Nervous system. I like that.
Synchronization primitives like mutexes and semaphores are for coordinating access to shared resources, making sure tasks don't step on each other's toes, data-wise.
Right, avoiding conflicts.
And for communication, there are things like queues for sending messages between tasks, or maybe direct-to-task notifications for really lightweight, fast signals. These aren't just features, they directly impact the integrity and predictability of the whole system.
Got it. So what about memory? You mentioned efficiency before.
Right. Memory management and protection. This is critical because embedded systems often have very limited resources. So memory allocation needs to be incredibly predictable.
How do they manage that?
Often, memory is allocated statically at compile time. Highly predictable, no surprises at runtime.
But less flexible, I imagine.
A bit less flexible, yes. Some use dynamic allocation, but it can lead to unpredictability and fragmentation, so it's often avoided in really safety-critical systems. Or they might use hybrid approaches, like memory pooling.
Tooling.
Yeah, pre-allocate large blocks, then divide them to smaller fixed-size chunks. Gives you some flexibility, keeps it predictable.
And protection. How do they stop one task from messing up another's memory?
That's where specialized hardware often comes in, like memory protection units, MPUs, or memory management units, MMUs.
Hardware help.
Exactly. The hardware helps the RTOS define memory regions with specific access permissions. So if one task tries to access memory it's not supposed to, the hardware steps in, generates an exception, and prevents it. This isolates faults.
Ah, I see.
The impressive part here is that robust memory protection isn't just software magic. It's a critical partnership between that specialized hardware and the RTOS kernel. This codependency is what allows for fault isolation and integrity, which is absolutely crucial for safety-critical systems.
So the hardware choice matters a lot too.
Hugely. And finally, there's interrupt handling. Interrupts are those immediate CPU signals demanding attention, right? They're handled by special functions called interrupt service routines, or ISRs.
Okay.
ISRs must be incredibly brief and efficient. The core goal for an RTOS is minimizing interrupt latency, guaranteeing a maximum bounded time for all interrupts to be serviced. Speed is vital, but here's the catch. ISRs often operate in a privileged mode, meaning they can sometimes bypass standard memory protection.
Yeah, that sounds risky.
It can be. A buggy ISR could potentially compromise the entire system. That inherent risk means ISRs must be kept extremely brief, with any complex processing deferred, pushed off to a regular task. It's about safely achieving speed within a tightly controlled environment. This really impacts how a safety-critical RTOS gets certified.
Wow. Okay. A lot goes into making these things work reliably. So it sounds like real time isn't just one thing. You mentioned safety critical. How do we classify these systems based on sort of their urgency?
You're absolutely right. Real-time is definitely a spectrum of criticality, not just a simple on-off switch. And this classification is key because it directly dictates the engineering rigor needed and ultimately the RTOS choice.
Okay, what are the categories?
Well, first we have hard real-time systems. For these, a missed deadline means total system failure, period.
Total failure.
Like catastrophic loss, major equipment damage, or even injury or loss of human life.
Yeah.
There is absolutely zero tolerance for delay.
Wow. Examples.
Think flight control in an airplane fly-by-wire systems, pacemakers, airbag deployment in your car, critical industrial robots operating on an assembly line, nuclear reactor controls.
Okay. Truly critical stuff.
Absolutely. These demand strict, guaranteed predictability and are almost always safety critical.
Got it. What's next?
Then we move to firm real-time systems. Here, infrequent misses might be tolerable, but they still lead to a degradation in quality of service. The key idea is that the usefulness of the result effectively becomes zero after its deadline.
So an old answer is a wrong answer.
Precisely. An outdated stock price is useless, right? They have less delay tolerance than soft real-time systems, but the system might still continue to function, just not optimally.
Examples for HERM.
Things like online trading platforms, maybe online auction systems, or even GPS navigation, where a slight delay might just mean a recalculation or a missed turn, but not a disaster. Airline reservation systems, too.
Okay, makes sense. And the last category.
And finally, soft real-time systems. For these, the usefulness of a task output degrades after the deadline. But the system itself keeps going. There's no catastrophe or total failure if a deadline is occasionally missed.
So performance just gets a bit worse.
Yeah, exactly. They have flexible timing and are more tolerant of degraded operation, especially during peak load. Often, they prioritize flexibility or overall throughput. Your personal computer is a great example.
My laptop, yeah.
Audio-video streaming, online video games, web browsing, these are all classic, soft, real-time applications. If a video frame drops, it's annoying, but the video continues.
Right. That spectrum is incredibly important. It really highlights that the real-time system controlling, say, your pacemaker is fundamentally different in its design, its rigor, its consequences from the one managing your smart home lighting.
Couldn't have said it better myself. The stakes are just completely different.
So given these unique capabilities and those really strict timing requirements, where do RTOS actually show up in the real world? It sounds like they're the silent orchestrators behind so much that's truly critical.
Indeed they are. Their deterministic and real-time capabilities make them absolutely indispensable across a huge array of industries. The automotive sector is just packed with them.
Like where in the car?
Oh, everywhere. Electronic control units, ECUs, managing your engine's ignition and fuel injection, often these follow the AUTOSAR standard. Then you have advanced driver assistance systems, ADS, and autonomous vehicle functions.
Collision avoidance, lane keeping.
Exactly. Those safety-focused ADS features absolutely rely on hard real-time responses. Anti-lock brakes, airbag deployment. Those are the quintessential hard real-time applications where milliseconds literally save lives. Adaptive cruise control, even infotainment systems use them, though maybe softer real-time for the infotainment.
Interesting.
What's truly fascinating in automotive right now is the rise of mixed criticality systems. You have functions like airbags, which are hard real-time, needing absolute guarantees, coexisting on the same physical processor as, say, the infotainment system, which is soft real-time.
How does that work safely?
It forces RTOS designs to implement things like adaptive partitioning and robust spatial and temporal separation, effectively creating isolated, protected zones for different levels of criticality on the same chip. It's complex, but essential.
Wow. Okay, what about aerospace?
Aerospace and defense, yeah. The stakes are arguably even higher there. RTOS enabled everything from avionics and flight control systems, autopilots, radar processing, fly-by-wire.
Fly-by-wire, right.
To missile guidance systems, complex radar systems, UAVs or drones, satellite control. NASA famously used VQuirks for many missions, including the Mars rovers.
Incredible.
In this sector, it's not just about being fast, it's about provable real-time performance and guaranteed security. Certifications, like DO-178C for avionics software, are absolutely non-negotiable. The RTOS has to meet incredibly high standards of assurance.
Makes sense. And medical. You mentioned pacemakers earlier.
Yes, medical devices are another critical area. Pacemakers, insulin pumps, ventilators, cardiac monitors, complex diagnostic equipment like MRI machines. These all rely heavily on RTOS for reliability, predictability, and minimal latency.
Life support systems, essentially.
In many cases, yes. And with the trend toward connected health, the Internet of Medical Things, or IoMT, These RTOS must also integrate secure networking capabilities without compromising that core real-time performance or patient data safety. Security is paramount.
Absolutely. What about factories? Industrial settings?
Industrial automation is a huge user of RTOS. They enable the precise motion control required in manufacturing robots and CNC machines. They ensure accurate timing on high-speed assembly lines, manage process control systems in places like power generation plants or water treatment facilities.
PLCs and things like that.
Exactly. Programmable logic controllers, PLCs, and SCADA systems often run on RTOS. They're also increasingly used for collecting real-time sensor data for predictive maintenance, feeding into AI and machine learning algorithms for building smart factories. The whole Industry 4.0 vision.
So an RTOS is literally the backbone enabling the factory of the future. That's a powerful role.
Absolutely. It's the essential low-latency foundation for collecting all that sensor data and executing precise control actions, feeding the intelligence that makes those smart factories truly smart.
Okay, we've covered the heavy-duty stuff. What about things we use every day? Consumer electronics.
Oh yeah, consumer electronics and IoT are full of them too, just maybe different types of RTOS. They're in smartphones, often helping manage background tasks or modem communications for better responsiveness. Wearables like fitness trackers or smartwatches rely on them for activity tracking, health monitoring, and especially for low power consumption.
Battery life is key there.
Totally. Countless IoT devices, sensors, smart home hubs, gateways often run an RTOS because they have very limited resources. Even smart appliances or components of smart city infrastructure, like intelligent street lamps or traffic management systems.
So they're scaled down for those applications.
Yes, exactly.
Yeah.
The challenge here is delivering rich features and a seamless user experience within extremely tight constraints. Very little RAM, maybe a slower CPU, and always needing to conserve power. This pushes RTOS designs towards extreme modularity and advanced power management features, like tickless idle modes, to make batteries last as long as possible.
Tickless idle.
Yeah, basically allows the system to sleep more deeply for longer periods when there's nothing to do, saving power compared to waking up constantly just to check the time.
Clever. Okay, one more area, telecom.
Right, telecommunications and networking. RTOS are absolutely fundamental here. Network routers and switches need them for rapid packet processing with minimal jitter to ensure smooth data flow. The infrastructure behind 5G networks relies heavily on RTOS to handle the ultra-high speeds and meet the ultra-low latency requirements.
Low latency is critical for 5G, right?
Absolutely critical. VoIP systems, base station controllers and cellular networks, satellite communication systems, they all use RTOS. In this context, real-time directly translates to quality of service, QoS, and overall network reliability. The RTOS guarantees that network performance, ensuring data packets are processed within strict deadlines, even under heavy load.
It's incredible just how pervasive these systems are, touching almost every aspect of technology.
It really is. They're the unsung heroes.
We've seen how essential RTOS are, but clearly there's no single best one, right? You've mentioned a few names. How do engineers actually choose among them? What are the trade-offs?
You're absolutely right. There's no one-size-fits-all solution. The optimal choice always depends on the unique demands of a specific project. You have to consider its real-time requirements. Is it hard, firm, or soft? How scalable does it need to be? What hardware is it running on? What are the development tools like? And, of course, budget and licensing costs play a huge role.
Okay, so can we maybe look at a few of the big players? Compare them a bit.
Definitely. Let's start with maybe the most widely known open source one, FreeTS.
FreeTSS, okay.
It's hugely popular, open source under the MIT license, and importantly, it's backed by Amazon Web Services, AWS. It's specifically designed for microcontrollers with very limited resources. We're talking tiny. It can run in maybe just over a kilobyte of RAM.
Wow, that's small.
It is. Its big strengths are obviously its cost effectiveness, no licensing fees, a massive and really active community, tons of documentation, and it's generally considered relatively simple to integrate and learn. It provides predictable timing, it's highly portable across different hardware, and it integrates really well with AWS IoT services, which is a big plus for connected devices.
What are the downsides then?
Well, traditionally its main weakness, especially for higher integrity systems, is that it operates in a shared memory space. That means less robust memory protection between tasks compared to systems that use hardware like an NPU or MMU. It also might have fewer built-in hardware drivers compared to some commercial options.
So where would you typically see FreeTS?
You'll find it everywhere in low-power IoT devices, battery-powered wearables, simpler industrial control systems, consumer electronics, and just general-purpose embedded applications where cost, simplicity, and maybe that AWS integration are the key drivers.
Okay. What about a more heavy-duty option?
Right, let's talk about VxWorks. This is a high-performance commercial RTOS from Wind River Systems. It's a real veteran in the field, been around since 1987. It's renowned for its reliability, its scalability, and rock-solid deterministic performance.
Used in those critical systems you mentioned.
Exactly. Its strengths are its decades-long proven track record in mission-critical applications. Think aerospace, defense. It offers incredibly strong, real-time performance and, crucially, comprehensive certification support for the most rigorous safety standards, like DO 178C in aerospace or ISO 26262 in automotive. It also boasts robust built-in security features and supports things like ARIN and C653 partitioning, which lets you securely separate different software components, even with different criticality levels, on the same processor.
Sounds powerful. What's the catch?
The main catches are cost. It's significantly more expensive than open source options due to licensing, and it generally has a steeper learning curve. The community is also smaller than, say, FreeTOS.
And its typical applications.
You'll find VxWorks in aerospace and defense missile guidance, avionics, high-end medical devices, complex industrial automation, advanced automotive systems like ADS or some infotainment platforms, telecommunications infrastructure, basically any mission-critical, safety-critical system demanding the absolute highest levels of reliability and certifiability.
Got it. You also mentioned QNX earlier with the microkernel.
Yes, QNX Neutrino from BlackBerry. It's really distinguished by that robust microkernel architecture. This gives it exceptional reliability and strong security advantages.
How does the microkernel help so much?
Because the core kernel is tiny, and most OS services, drivers, file systems, networking stacks run as separate, memory-protected processes in user space. So if a driver crashes, it typically doesn't take down the kernel or other critical components. That isolation is huge for fault tolerance.
Ah, that isolation again.
Exactly. QNX also offers robust layered security features, high determinism, and adaptive partitioning to ensure critical processes always get the CPU time they need, even under load. It uses a message-based system for inter-process communication, which promotes a really clean, decoupled architecture, and it has a true process model with protected virtual address spaces, much like a desktop OS, but engineered for real-time.
Downsides.
Historically, it might have had a slightly heavier footprint than some of the ultra-lightweight RTOS, though that's evolving. There's a higher initial investment compared to open source. And it wasn't traditionally focused on things like complex graphical user interfaces, although that's changing too, especially in automotive.
Where is QNX strong?
It's huge in automotive, particularly for infotainment systems, digital cockpits, ADS, and active safety systems where reliability is paramount. Also strong in aerospace and defense, medical devices, industrial automation, and telecommunications gear like base station controllers or network switches. Anyway, reliability, safety, and security are top priorities.
Okay, are there other major open source players besides FreeTOS?
Oh, yes. A really important one now is Zephyr RTOS. It's open source, scalable, and backed by the Linux Foundation, which gives it significant industry support. Its big emphasis is on openness, portability across hardware, modularity, and crucially, security.
Security focus, how so?
It's designed with a security-first approach. Things like secure boot capabilities, support for hardware-assisted memory protection, integrated cryptographic libraries. It's also highly modular and configurable. You can scale it down to run on devices with maybe just 8 kilobits of flash and 5 kilobits of RAM, or scale it up for more complex systems. It has a rich connectivity stack built in for things like Bluetooth, Wi-Fi, Thread, Zigbee, making it great for IoT, and it supports multiple processor architectures and is vendor neutral.
Strengths seem clear. Any weaknesses?
Well, its kernel is generally more complex than something super simple like FreeTOS, which can mean a bit more overhead in terms of scheduler latency or context switching time in some configurations. Because it emphasizes strong task isolation, it might be slightly less RAM efficient than simpler shared memory models in certain use cases. And like QNX, it's not really designed for graphically demanding user interfaces or heavy multimedia.
Typical uses for Zephyr.
It's gaining a lot of traction in IoT devices. Sensors, wearables, smart home tech, industrial automation, automotive applications, especially for sensing and control modules, healthcare, and worker safety equipment. It's also well suited for multi-core embedded designs.
Interesting. One more. Maybe something else lightweight.
Sure. Let's mention RT-Thread. This is another open-source, lightweight embedded, real-time multi-threaded OS written in C. It's particularly known for its extremely compact kernel. Its nano version can run in as little as 3 KB of flash and 1.2 KB of RAM.
Even smaller than FreeTOS minimums. Wow.
Yeah, it's very resource efficient. It's open source with an active community, offers strong real-time performance, and it's designed to be flexible and customizable with a kind of modular, object-oriented design approach in C. It's also generally easy to port to different hardware.
And the trade-offs for RT Thread.
Its main challenge might be a less mature or extensive ecosystem of pre-built drivers and middleware compared to giants like RTOS or even Zephyr. It might lack some of the very advanced features found in the high-end commercial RTOS. Debugging tools might also be less extensive than for some others.
Where does it fit in?
You'll see it used in smart homes, some industrial automation tasks, automotive electronics, maybe less critical functions, and especially in very resource-constrained IoT devices where that tiny footprint is the most important factor. Also used in general embedded systems development.
This truly illustrates that choosing an RTOS is a really deep strategic decision. It's not just picking a tool off the shelf. It's about perfectly matching the capabilities, the constraints, the safety requirements, the cost model, matching all of that to the specific task, with huge implications for everything from development time and cost to system safety and the ultimate performance the user experiences.
Exactly right. It's a foundational choice that impacts the entire project lifecycle and the final product success.
Well, what a deep dive into the world of real-time operating systems. It's crystal clear they're far more than just lines of code. They are absolutely the foundational components enabling everything from pacemakers keeping us alive to autonomous cars navigating our roads, working with incredible precision and reliability, all silently behind the scenes.
Absolutely. They truly are the silent orchestrators, ensuring systems respond predictably and within those guaranteed timeframes. That precision isn't just about efficiency. It's fundamental for safety, for security, and for the reliable performance across countless industries that, frankly, we now depend on every day.
And what's fascinating is watching their evolution with these trends, like microkernel architectures becoming more common, the constant enhancement of security features, and the sophisticated ways they manage these mixed criticality systems. It means they're only becoming more complex, more robust, and even more vital to our technological future.
Yeah, and if we zoom out and try to connect this to the bigger picture, you see the increasing complexity and autonomy in embedded systems everywhere,
Yeah.
especially with the integration of AI and machine learning right at the edge.
Right, AI on the device itself.
Exactly. It means RTOS will continue to evolve not just as operating systems, but more like comprehensive safety and security platforms.
Yeah.
They're not just running the code anymore. They're actively safeguarding our interaction with these increasingly intelligent autonomous machines.
So what does all this mean for you listening right now?
Well, as these embedded systems become even more interwoven with our daily lives, and as their complexity and their criticality continue to grow, understanding this underlying real-time foundation becomes more important than ever, even if you're not an engineer.
The next time you see a robot moving precisely in a factory, or you ride in a new car with advanced safety features, or even just interact with a smart device that responds instantly, take a second and remember the RTOS silently working inside, ensuring everything happens exactly when it should.
It really makes you wonder, doesn't it? What other unseen technologies are shaping our future in such fundamental ways, operating just below the surface of our everyday awareness?
That is a perfect thought to leave you with. Join us next time for another deep dive into the fascinating world of knowledge.